What's up guys, welcome back to the next video in learning algorithms. My name is QDS Danny and you guys watching my channel Crowwood. Alright, so in this video we're gonna see asymptotic analysis. What is asymptotic analysis? So if you guys not familiar with asymptotic, asymptote came in from mathematics and it's asymptotes. So what is asymptote? So I'll give you guys the quick definition of asymptotes so you guys be familiar. But if it doesn't make sense to you guys, it means that you guys you're not going to understand asymptotic analysis and asymptotic notations. So if you guys don't understand the analysis and notation, then it doesn't make sense to you guys anything big O notation or omega notation or theta notation. So asymptotes in mathematics is a straight line that constantly approaches a given curve but does not meet at any infinite distance. In other words, so asymptote is a line that the curve approaches as it meets as it moves towards infinity. So for example, we have our x-axis and y-axis. So that's our y, and this guy here, that's our x, and we have a curve that's coming, say for example, I'm gonna put it like that, and the curve is coming like from the top, and this curve is coming this way. Okay, so and we have our asymptotes here, and that asymptote is gonna be a line, and that moves along this curve. Okay, so now this is our curve. So this, and that's our asymptote. This guy here is our asymptote. So the curve visit asymptotes but never overtakes them. And if you look in here, it never overtakes them. The method we find the horizontal asymptote changes involve pairing the degrees of polynomials in the number of denominators of the function. So what it means, what we mean by asymptote? Asymptote means, say asymptote of the curve y is equal to f of x. So we have a y of f of x, function of x, our implicit form, if xy is equal to 0 is a straight line such that the distance between the curve and the straight line lends to 0 when the points of the curve approaches infinity. And there are three types of asymptotes. Asymptotes in mathematics, there are vertical asymptotes, there are horizontal asymptotes, and the last one is going to be oblique asymptotes. So and I'm quickly gonna show you guys that's the first one is gonna be horizontal asymptote. So that's gonna be your y axis, and that one's gonna be your x-axis. And here we are talking about horizontal. I'm just gonna put the first word asymptotes, and the horizontal asymptote is gonna come from the y like that, and goes towards x infinity, and you guys gonna see the asymptotes gonna come like that. So from here like that. All right, so and this guy here is asymptote here. All right, so this one's horizontal, and then the next ones we could have the vertical. And vertical is I'm gonna put it like a VA. That's vertical, and if it's gonna come like that, that's gonna be our y-axis, and this guy is gonna be our x-axis. And you guys gonna see a curve gonna be like that. That's our curve. All right, and the asymptote for the vertical is gonna be like this. and that's gonna be our asymptote. Alright, so finally the oblique one's gonna be, so I'm gonna put the oblique one, and that's gonna be our y-axis, that's gonna be our x-axis, and you guys seen this one here is horizontal, you guys seen this one here is vertical, and the oblique one's gonna be, say, from here, it's gonna be like that. So this one's gonna be oblique, and you guys gonna see the line, or this our asymptote is gonna be like that. So it's gonna be a straight line, because this our curve is approaching this our line, so that's gonna be asymptote, and this is the curve, that's gonna be, this is gonna be put a C, and this one's going to be gonna put a, because that's gonna be our asymptote. So this is the asymptote, and how we're gonna see asymptotic analysis. And the next video I'm gonna show you guys what we mean by asymptotic notation, because if you guys look in here, we have a curve, and we have a curve, then we have a straight line, and that's exactly, it's the same idea. It's the same idea in algorithms when we say asymptotic analysis, because they're going to be input, say we put an input, say our input's going to be 1, 2, it's going to be 3, all the way to n, whatever numbers you guys want to put, because the number is like that. Then we're going to denote that input as f of n, because that's going to be the input, whatever input. Say with this one's going to be, if it's 1, 2, 3, it's going to be a lot easier, it's faster for computer. But what happens if the input grows? What happens if we increase the input? Then we're going to see the rate of the growth. We're going to how long it's going to take for algorithm to process this one. So imagine if it's 1, 2, 3, it's going to be a lot easier for any computers to do this one. Imagine if it's a million, or say 10 million or 10 billion numbers. Then what happens with the computer? How the computer is going to cope with this one? So now in the asymptotic analysis, we're going to see the speed. What speed is that? It depends for a lot of things. For a computer, which computer is that? If any computer, or just going to slow computer, it depends on a lot of things. So we're going to see this in this video. In the next video, we're going to go on asymptotic notation. We're going to see what notation is, and then we're going to see all the different factors. Okay, so we're going to remove this. Now that we know that what is asymptote in mathematics, we're gonna start our video. Then we're gonna see that we've seen the running time. What is the worst case running time in the previous video? So we have discussed in depth about the running time, but it says it depends. The worst case, it depends what sort of computer we are talking about. We are talking about the Google's supercomputer, or my old computer. So which computer we are talking about when we say worst case running time? So, and we come in at the end, we say it depends. It depends on two factors. The first one, if we compare the speed, and it depends on the machine. The first one, we're going to get the relative speed on the same computer, and the second one, we're going to say the absolute speed on different computers. So our algorithms here on when we say relative speed on our computer, say on old computer, or we have a very fast computer, but it's not the same as going to be on any other computer. So if I want to run it on different computers, then it's not going to be the same as my computer. So if we're running on say Google's supercomputer, then it's going to be, of course, it's going to be fast. But what happens if it's on different computers? Then if our algorithm is not going to run on every computer, then we're going to say that's a relative speed. And when our algorithm runs on every computer, I mean every devices and every machines, then we say that's the absolute speed. So that we have two speeds in asymptotic analysis. That's asymptotic analysis. We're going to see the worst case running time. So, and then we're going to see that when we talk about an asymptotic analysis, then we're going to say why algorithms are so successful. And algorithms are so successful is because our ability to take a very big complicated situation and reduce it to do some simple mathematics. We adopt some mathematic notation to help us, and that notation is asymptotic notation, as I said to you guys before, and I have shown you guys the asymptote. And as I said to you guys that asymptote is a straight line that constantly approaches a given curve but does not meet at any infinite distance. So, and we say that asymptote is a line that the curve approaches as it moves towards infinity. And that's because we're gonna see a big complicated situation and reduce it to do some simple mathematics. We adopt some mathematic notation, and that notation is going to be asymptotic notation. That's what we mean by asymptotic. We use asymptotic notation to describe the running time of the algorithms, and that's what we mean. What is the worst case running time? And that's what we say, use asymptotic notation to describe the running time of algorithms. Alright, so we continue our algorithms. So we're gonna see asymptotic notation, and asymptotic notations are used to represent the complexities of algorithms for asymptotic analysis. The notation we use to describe the asymptotic running time are defined in terms of functions whose domains are a set of natural numbers. And if you guys are going to see here, then I'm going to repeat that again. The notations we use to describe the asymptotic running time are defined in terms of functions whose domains are the set of natural numbers. And that's the natural numbers. That's how we're going to describe the domain of asymptotic running time. Such functions are convenient for describing the worst case running time function of T of n. The core idea of algorithm is to represent the resources we are analyzing, usually time but sometimes memory, as function, with the input size as its parameter. We ignore the machine dependent constant, ignore the running time, and you look at the growth of T of n as n approaches the infinity. So that's how we're going to see this one. If T of n as n gets towards the infinity, we ignore machine dependent constant, so ignore the running time, and we look at the growth of T of n as n approaches infinity. Alright, so in this video we've seen the asymptotic analysis and we've seen the asymptotic notation. In the next video we're going to discuss the most important aspects of asymptotic notation, and we're going to see the growth, we're going to see the worst case running time, and we're going to see the big omega, big theta, and big O notations. So we have seen asymptotic analysis and asymptotic notation, and as we said, I'm going to repeat again, the notation we use to describe the asymptotic running time are defined in terms of function whose domain are a set of natural numbers. Just remember that one. And we ignore the machine dependent constant, ignore running time, and look for the growth of T of n, and that T of n is the input as the n approaches the infinity. And next video we're gonna see in depth what is f of n and what is g of n, because we have two functions of f of n, which is the input, and we have g of n, and we're going to see the big O notation, we're going to see the omega notation, when we're going to see the theta notation. So the big O is upper bound, the omega is lower bound, and the theta is upper and lower. So, and we're going to see that in the next video. Alright guys, that's it for this video, and I'll see you guys in the next video, and bye.